For over 5,000 years, Egyptian civilization was shaped by a physical reality. Wherever the Nile River flows, people can settle and farm. This river used to be the only water source, but today, that reality is turning into an extremely harsh geographical trap. Look at the actual statistics. 96% of Egypt's land area is an arid desert. Over 113 million people are currently crammed into a narrow strip of land, making up just 4% of the country's area along the banks of the Nile. This spatial overload is reaching its technical limit, especially since the population is expected to grow to nearly 175 million by 2050. Additionally, every year the country loses 2% of its agricultural land due to urban expansion. They are gradually losing surface land for farming, while having to provide a massive amount of food for millions of new people. Facing the risk of a complete collapse of the food security system, the Egyptian government decided to act. They are launching the largest-scale engineering project of the 21st century, the New Delta megaproject. Their core goal is not just planting trees, but building the world's largest artificial river to directly transform the desert surface into agricultural land. Before we dive into analyzing the technical blueprints of this megaproject, please take a few seconds to hit the like and subscribe buttons. Your support is our biggest motivation to continue making in-depth analysis videos about fascinating engineering projects like this. Let's get started right now. When analyzing this project, we will see that this is not a symbolic structure, but an urgent national security strategy. Egypt's economy is facing a tough problem. They are one of the world's largest wheat importers, relying on supply chains thousands of miles away for over 50% of their food. This weakness became clear in 2022, when the global supply chain faced a severe crisis. The supply disruption caused wheat prices to soar by nearly 40%. This price shock put a massive strain on the national budget, forcing Egypt to solve the problem of real food self-sufficiency. Upstream on the Nile, Ethiopia's completion of the Grand Renaissance Dam also created major changes to the natural water flow. Faced with geopolitical shifts in climate change, making the Mediterranean region increasingly arid, Egypt was forced to actively restructure its agricultural map. The New Delta project was launched with the goal of reclaiming 9,200 square kilometers of the western desert surface. This area is equivalent to the entire island of Cyprus and is expected to help increase the country's total agricultural land by 25%. To make this a reality, engineers are deploying an irrigation infrastructure network of an unprecedented scale in the region. The backbone of the project is a 114-kilometer-long artificial water transmission route running parallel to the Nile. Unlike traditional canals, this is a complex water circulation system, combining open-air canals and a network of high-pressure underground pipes. In the underground sections, construction crews must dig deep technical trenches. Steel pipe sections with a diameter of 3 meters are lowered to the bottom, welded together using automated technology and coated with anti-corrosion materials before being covered with soil. The biggest geotechnical challenge lies in the open-air canal sections. Desert sand is highly loose and very prone to landslides during excavation. To ensure stability, engineers create gentle slopes and use geotextile membranes for reinforcement, then bring in a slip-form paver system for construction. This system operates continuously, moving along the canal route and extruding a seamless concrete wall with high precision. However, the climate challenge in the desert poses a complex material problem. Under temperatures that can reach 50 degrees Celsius, the water in the concrete mixture will evaporate very quickly. A hydration process that happens too fast will cause the surface structure to crack. To overcome this, mixing stations apply hot weather construction standards, including using crushed ice instead of liquid water, combined with spraying liquid nitrogen to lower the aggregate temperature to a safe level. At the same time, most of the concrete pouring work is shifted to the night shift to avoid direct impact from solar radiation. The final and most complex physical barrier is the difference in elevation. The desert terrain at the project slopes upward against the direction of the water flow. To deliver the water to its destination, the system uses 12 supercapacity pumping stations distributed along the route. These stations are responsible for pumping water over an elevation difference of more than 100 meters, equivalent to a 30-story building, operating continuously 24/7. Transporting millions of cubic meters of water against gravity creates massive hydrodynamic pressure. If the pumping system suddenly loses power, the massive volume of water will rush backward along the pipeline, causing a water hammer shock phenomenon. This instant pressure can rupture the steel pipe structure. Therefore, the entire transmission network must be equipped with pressure relief check valves and specialized surge tank systems to absorb the impact force. But the core technical question is, where does this massive water source come from? Egypt cannot arbitrarily extract more water from the Nile due to concerns over international water-sharing conflicts. The solution to this problem is the Al Hammam water treatment plant, a facility currently holding a Guinness World Record. Completed at a lightning-fast pace in just 2 years and officially operating since mid-2023, this is the largest agricultural wastewater treatment plant on the planet. Every day, this complex has the capacity to process up to 7.5 million cubic meters of water. Operationally, the system collects agricultural wastewater from the northern region, which contains high salt concentrations and pollution levels. Instead of wasting this water by discharging it into the sea, the plant cleans the entire flow and pumps it back into the desert. Many people mistakenly believe a massive project like this would use RO microfiltration membranes, also known as reverse osmosis technology. But the technical reality is completely different. RO technology requires immense pressure and consumes a massive amount of electricity. If RO were used to filter 7.5 million cubic meters of water every day just for irrigation, the operating costs would collapse the entire project budget. Instead, Al Hammam applies a high-tech physical, chemical, and biological treatment complex. First, the wastewater is pumped into giant flocculation clarifier tanks. Here, specialized chemicals are mixed in to catch mud, suspended impurities, and polluting molecules, forming large precipitates that sink to the bottom. The clear water on top continues through a multi-layer mechanical filtration system before undergoing high-intensity disinfection. This process ensures the output water is completely sterile and meets international irrigation standards, preventing poisoning of the new vegetation. Going deeper into the structural details, because it doesn't separate 100% of salt ions like an RO membrane, the water environment inside the plant still maintains a certain salinity and is highly corrosive to infrastructure. To maintain the facility's lifespan, engineers had to completely cover over 520,000 square meters of concrete surface with a premium industrial epoxy coating. This protective coating area is equivalent to dozens of football fields, a massive workload just to ensure that residual chemicals don't destroy the plant's core structure. Finally, besides recycled water, the project also taps into fossil groundwater from the Nubian sandstone aquifer deep underground. This combination creates a multi-layered water supply strategy to completely solve the country's water crisis. To control a massive infrastructure system stretching hundreds of kilometers across the desert, human effort alone is completely insufficient. If the open canals and pipelines are the physical body, then the SCADA system is the operating brain of this entire megaproject. SCADA, or Supervisory Control and Data Acquisition, acts as a central digital nervous system. In the control room, engineers can monitor every pumping station, every valve cluster, and every cubic meter of moving water in real time. Imagine if one of the 3-meter underground pipes experiences a pressure drop 80 kilometers away in the middle of the wasteland. The sensor system will immediately send a warning signal back to the center. This automated intervention and close monitoring help turn a massive artificial river into an engineering utility with absolute precision. And once the water safely reaches its destination, the farming process is also maximized in automation. Satellite imagery from NASA and Google Earth has recorded an astonishing geological transformation on the desert surface. Massive green circles are appearing increasingly dense amidst the sea of yellow sand. That is the signature of the center pivot irrigation system. Instead of wasteful flood irrigation, this technology uses a central water supply tower connected to a spray boom hundreds of meters long. This boom is equipped with wheels driven by electric motors, moving continuously in a circle to distribute water over a vast circular area. Thanks to the integration with the SCADA system, agricultural engineers can precisely regulate every drop of water and dissolve fertilizer right to the plant roots, minimizing the evaporation rate under the scorching Sahara sun. However, intervening in infrastructure to force nature to change always comes with massive costs. International environmental experts have begun to sound the alarm. The most dangerous technical risk of this project is not the lack of water, but the surface chemistry problem: salt. The nature of desert soil already contains high natural salt levels, plus the fossil groundwater also carries many minerals. Under the scorching heat of the Sahara, as irrigation water evaporates rapidly, capillary action will draw salt ions up from deep below and leave a white layer of sediment on the surface. If the drainage system isn't perfectly designed to wash away this salt, all these billion-dollar fields will quickly be desertified back into barren salt flats in just a few seasons. Next is the immense financial pressure. The total investment for this mega project is estimated to range from $10 billion to $25 billion. This is a massive infrastructure burden for Egypt's already heavily strained economy. Furthermore, the 12 giant pumping stations tasked with pushing water 100 meters uphill consume an enormous amount of electricity. The energy bill to maintain this system will be a permanent fixed cost, draining the budget. That is exactly why the project is undergoing a strategic shift in farming. Instead of focusing solely on growing wheat to ensure food security as the initial core objective, a large area is being zoned to grow high economic value export crops. For example, in the Fayum region, a series of high-tech greenhouses have been set up to grow bell peppers, mangoes, citrus fruits, and premium medicinal herbs to bring in valuable foreign currency to offset operating costs. This move is generating multi-dimensional technical debates. Is shifting to export crops a smart business move to keep the project alive, or a deviation from the goal of feeding the people? What do you think about this economic puzzle of Egypt? Leave your analytical opinions in the comments section below. The final puzzle piece of this mega project is the human resource issue. You cannot operate millions of hectares of high-tech agricultural land without a technical team and on-site workforce. To solve this problem, the government is building the new city of Jerion, dubbed the City of Flow. This is not just housing for workers, but a comprehensively planned megacity, with infrastructure designed to welcome about 3 million families to settle. The profound goal is to create a massive demographic shift, pulling millions of people out of the space-depleted Nile Valley to a new economic center in the heart of the desert. In June 2023, the project reached a historic milestone when the first treated waters officially flowed into the artificial river system, marking the start of a new era. This entire mega project is designed to be rolled out in multiple strategic phases. Phase 1 is currently heavily focused on completing the core water transmission infrastructure network, finishing the supercapacity pumping stations, and conducting the initial desert soil treatment and reclamation process. Moving into phases 2 and 3, the scale of the project will be significantly expanded. The workload will not stop at increasing agricultural land area, but will also include building specialized food processing centers. Along with that is a modern logistics network designed to directly connect these desert farms with the country's major seaports. President El-Sisi has called this massive effort the future of Egypt. This is truly a decisive gamble aimed at completely redrawing the economic and agricultural map of North Africa. If this infrastructure network operates successfully, the new delta will become a global testament to the ability to apply engineering to overcome harsh environmental conditions. On the contrary, if the geological, chemical, or financial calculations fail, it risks becoming one of the most expensive structural ruins in modern history. Ultimately, only time and the actual stalks of wheat growing from the desert sand can provide the most accurate answer. This project is an incredibly bold engineering test, a proof that the combination of irrigation infrastructure, digital technology, and urban planning is striving to conquer the harshness of the Sahara. Thank you for joining us in this video. If you are passionate about technical analysis of giant megaprojects around the world, please hit like, share, and subscribe to motivate us to produce upcoming content. Goodbye and see you next time.